last week on Patterson maps. And we'll be continuing a little bit on Pattersons today. And we ended with this slide, okay, which shows you some examples of what you would see in a Patterson map for certain real space crystal structures. And this picture over here is actually fairly important because it already shows you a little glimpse of how things are used in a Patterson map. Here are two atoms that are given with positions. And then your interatomic vectors can be given with respect to the distance between these equivalent positions. Now, do you usually use your measured intensities directly to plot a Patterson? As a matter of fact, in many cases people use something else. They use something called E-values. And the E-values are intimately related to the F values. The main difference is they are normalized. Okay? And what the normalization does is it removes the drop-off of your F's, of your small f's, your atomic scattering factors as a function of angle. As you might recall, especially from the one homework set, you have this drop-off in F as a function of sine theta over lambda. And it also removes the thermal motion. So what an E value is basically the F value divided by the sum of all small fj squared, where this one contains both the F that comes from the atom and this term from thermal motion. So the advantage is that your data often looks a little bit cleaner when you do that one, and that's why people prefer working with E values, not with F values. Now, what kinds of Patterson maps do you usually get? As I said just a moment ago, often you get some that are done with E values. There are several ways of plotting those. Sometimes you get E squared maps, okay, just similar to F squared, where F squared would be the intensity. And sometimes you get E squared minus 1 maps, okay. The difference between these is that this one removes the origin peak. Remember, every atom has the shortest distance to itself, so you get this big peak at the origin. Now if you normalize for all of your atoms, what will happen is if you subtract 1 from each E squared, you will actually end up with a map that doesn't have an origin peak. You still get positive features because remember, these signs mean it's the magnitude. Okay? So, E squared minus 1, pretty popular because it gives you maps without an origin peak. E squared gives you extremely sharp peaks. Okay? One word of caution, if you sharpen your map too much, you can actually get some spurious peaks that really shouldn't be there, because remember, you have truncation errors. You do not have the full Fourier series. So what does this look like? Here's a map that is just plotted as a function of the F squareds. Here's what you get if you plot the E squared minus 1 values. Okay? This big origin peak, which tends to swamp certain things, is gone. And instead, you get a bunch of peaks. And I don't think anybody would have trouble to identify the 3 strongest peaks in this map. Right? This one, for example, was swamped by the origin peak before. You can still tell that there's something here, but it would be more difficult to locate that peak. Now, what do you usually look for when you look at a Patterson? Pattersons can actually be very important because you can look for what is called Harker lines and planes. Okay? What these lines and planes refer to is that often when you have a Patterson map, you will find that the strong peaks fall either along a line or in a certain plane. Okay? And Harker is the one who discovered this, so that's why they are called Harker lines and planes. Now, what that arises from is actually your space group symmetry. Okay? So, you can directly tell something about your space group by looking for Harker lines or planes in your Patterson map. Now that's obviously very powerful because, as we all know, finding out the space group of our material is one of the things that we definitely want to do. So, Harker lines. For example, if we have space group PM, nice monoclinic space group, we have 2 equivalent positions, okay, from this mirror plane. So what we get is that every atom at XYZ has an equivalent atom at XY bar Z. And we've used that before, right, for systematic absences. Well, we haven't done that with a mirror because a mirror wouldn't give you systematic absences. But here are 2 equivalent positions. Now that means for any atom at xyz, we have an equivalent atom at xy by z. If I have a heavy atom at xyz, there is another equally heavy atom at xy by z. And that interatomic distance between these two should show in the Patterson map, right? That is what a Patterson is all about. What is the distance between these two? Well, x minus x in vector space, that's 0. Y minus minus y, that's 2y. And z minus z, which is 0 again. So the interatomic distances between equivalent atoms will be 0, 2y, 0. Where y is the coordinate of each individual atom. Okay? That means in Patterson space we use UVW as our interatomic distance coordinates, remember? That means we'll have a Harker line 0v0. We'll have a lot of peaks there, because every single atom in that unit cell will generate a peak somewhere on this line depending on its y coordinate. Okay? Space group PC, equivalent positions would be xyz, xy bar z plus 1/2. Same deal. You form the distance between these coordinates. Okay? Once again, we are in vector space, so you just subtract the x, the y, and the z component from each other. That means you'll get peaks at 0, 2y, 1/2. Once again, that's a line. Okay? One of the coordinates happens to be 1/2 now, but there's only one variable, the 2y. So you have a Harker line 0v 1/2 along which you'll have peaks corresponding to every single atom in that unit cell with its symmetry equivalent atom. Now notice, mirror. How many dimensions does that symmetry element have? It's a mirror what? It's a two-dimensional element, right? It's a mirror plane. Glide, what is it? What do we call it? A glide plane, right? So once again, it's a two-dimensional element. The translation may only be in one direction, but it's a two-dimensional symmetry element. Both of them make Harker lines because they change one coordinate. Okay? Now, let's look at what happens when we have a one-dimensional symmetry element. Some kind of axis, rotation or screw axis. We get Harker planes. Okay? Why? Because now we have symmetry equivalent positions, x, y, z, and x bar, y plus 1/2, z bar. Okay? What's the difference between these? 2x, 1/2, 2z. So that means there are two variables in here, and you will get peaks along the Harker, in the Harker plane u 1/2 w. Same way you could do this with P2. Okay? In this case, you will get u 0w. Now this is pretty important because some of you asked me quite a few weeks back, okay, so we can use systematic absences to figure certain things out. How do I distinguish the rest of it? Right? Quite a few of you asked me that question. Well, here's a way. P2, systematic absences, yes or no? No, right? There's no translation in P2. P2-1 would have systematic absences, P2 doesn't. So, no systematic absences. Actually, you used it in your project, right? How about that one? Systematic absences? Mirrors give systematic absences? No, they don't, right? So neither PM nor P2 have systematic absences. But one of them will have a lot of peaks on a line 0v0. The other one will have a lot of peaks in a plane u0w. So, once you plot this Patterson, you should be able to get some idea of which of these space groups it is, right? Just by looking at that plane and at that line and figuring out which of those actually has a decent number of peaks. So these Patterson maps really can help you a little bit further. Remember, Patterson symmetry shows you rotations and mirrors. Remember how we looked at that example last week? So, you can distinguish the things that you cannot distinguish with systematic absences by other means. That's the answer to what we discussed a few weeks back when I told you we'll get there. Yes?
So how do you get the Harker part? I understand the Patterson. How do you subtract 2? How do you get the Harker plane? You just know that? Or
Basically, what I see here is that in my Patterson, I will have peaks at 2x, 1/2, 2z interatomic distances, okay? Which in Patterson space, I would of course call u. V is always 1/2, and w, right? Because that's, I don't use x, y, z, because they aren't real coordinates. I use u, v, w to represent the distances. If I have something that has 2 variables and 1 constant, that describes a plane. So that's why I call it a Harker plane. And Harker was the one who figured this out, so that's why it is named after him. Does that make sense?
Well, I was wondering how you get from 2x to u. Like if there was a thing.
Basically, this is a variable, okay? And this is the variable related to the real atomic positions. However, in Patterson space, I don't plot things as a function of 2x, or as a function of x for that matter. I plot things as a function of interatomic distance. So my coordinates in Patterson maps are u, v, and w. They correspond to these x, y, z values. And that is what you use when you use a Patterson. So, Harker lines, Harker planes, very useful. Good question is, how do you use a Patterson, right? And this gets right there, what do these things mean? What do we do with them? Usually a Patterson is used to actually locate the heaviest atom in the structure, okay? And that goes back to, remember how we said, every peak in the Patterson, the height is proportional to z times z prime, where z was the atomic number of the element, equal to the number of electrons. The heaviest atom will obviously have the highest z, and the height of the peak that corresponds to the distance of that atom to its symmetry equivalence is going to be z squared. Okay? Now, why does that help us? What good does it do us? Okay, we found a heavy atom. Well, first of all, we found an atom, so that's always good. Secondly, the heavy atom usually dominates the scattering, right? Because it contributes more. It has more electrons than everything else in that unit cell. So what we can do is we can go back to our original expression where we have no phases, remember? That is what we lose during data collection. And we can plug in the xyz coordinates of our heavy atom that we found from a Patterson map, okay, by using those u, v, and w equal to the interatomic distances relationships. And then we can actually calculate phases based only on the heavy atom. Are those the correct phases? No. They are not absolutely correct, but they are a much better approximation than having no phases, okay? Because that heavy atom is the strongest contributor to the phases. Yes?
Can that only be done once, or can it be done multiple times to try to get a better approximation?
Can that be done only once, or can that be done multiple times? Good question. You certainly will be refining things by adding more atoms and recalculating your phases. So with respect to that, absolutely, it's done more than once. Most of the time, you won't use your Patterson anymore at that point in time, okay? Because the difference is, now you can actually calculate some approximate phases, so you can calculate what is called a Fourier map, okay? You use those phases that you didn't have access to before, and you calculate your electron density maps. And then you work with those, because as I said, the assumption is your heavy atom dominates the scattering. The phases won't be absolutely right, but they'll be close enough to let you proceed. Okay? Once you have those, you calculate a density map. Now you look for other peaks. And now you're not dealing with interatomic distances, right? Now we are directly dealing with our electron density, so we can directly get our xyz coordinates off that map. So that's why once we have any kind of starting phases, we usually go for an electron density map, okay? Because that makes our life much easier. And we like life to be easy, don't we? Now, when do Patterson maps work well? Well, they work well if you have a fairly simple structure and one heavy atom. Okay? And that's kind of a flexible expression. What is fairly simple? What is heavy, right? Well, depends a lot on what your material is, okay? Small molecules, this often works very well, especially if you, for example, have a metal oxide. Because most metals are a lot heavier than oxygen, okay? Now, that said, if you have titanium oxide, okay, titanium, oxygen, yeah, titanium is a heavy atom. If you have something like barium titanate, barium, titanium, and oxygen, your titanium is no longer a heavy atom, okay? So it's all relative. It has to be heavier than everything else in the unit cell. So, back to Anthony's question, what do you do once you have that first atom? Well, you want to find more atoms because our structure usually has more than one atom in it. So, what you usually do is, after locating some initial atoms, you do a so-called Fourier difference map to locate the missing atoms. And of course, you really calculate those F maps and then you do the Fourier transform, so you look at electron density. It doesn't matter how you find your initial atoms. You will have to do some kind of Fourier difference map in order to find the rest of your structure, okay? The main difference is how do you get that initial atom and how do you get those initial phases. These kinds of maps are often called F0 minus FC or F-ops minus F-calc maps. So what are these maps? An F-ops map is a map that is calculated using your experimental intensities, which means you can get the structure factor magnitudes out of that, and phases that you get from some kind of structural model. And of course that means these are incomplete phases, right? These are the phases that have only the information from the atoms you've already located in them. What do these show? Well, they will show you peaks if there are atoms that you're missing in your model, okay? Because obviously that information is in your intensity data that you collected. And that means you can look at these peaks and locate more atoms, and that's what you want to do. An F-calc map all by itself is actually a pretty useless map. An F-calc map basically comes from using the phases and the amplitudes that you would calculate for a structural model. So all that it shows you is exactly the atoms that you've already put into your model in exactly the locations where you put them into your model. So, not very useful, is it? It's just a graphical interpretation of what you put into your model. But if you actually subtract one from the other, you get a very useful tool called a difference map, okay? So, you take measured and calculated Fs for the F-ops and the F-calc, and in both cases you use the calculated phases. When you subtract these from each other, you will get anything that is incorrect in your model. That means there will be peaks where there are atoms missing. If you put an atom somewhere that shouldn't be there, you'll get a deep hole, okay? Because basically your F-ops does not support that atom that is calculated. So you'll get something negative there. You don't want negative features in your difference maps, okay? That means something is wrong. Now, when you look at these maps, what do you need to keep in mind? Once again, an important word in X-ray diffraction is map resolution, or resolution in general. Remember we talked about that, data resolution, and what the Fourier transform looks like depending on what your resolution is? Well, we are still dealing with Fourier transforms, folks, so this still applies. In theory, you want a complete Fourier series, a complete Fourier synthesis for your map where you take all FHKL values. And that means from minus infinity to plus infinity for H, K, and L. We never get that, okay? It's just not possible. First of all, you can't measure all of them. Secondly, even if you could, would you really do it? No, we want to get done with that structure solution at some point in time, right? So there's a limit to how much we will measure. And given that we only have a finite amount of data, we are basically neglecting some of the high resolution data, and that will obscure some structural detail. It will also introduce some unwanted ripples. So while I just said you don't want any negative features in your electron density map, you will always have some very small negative features. Okay, that's unavoidable. The important thing is they should be small. And they are given in electrons per cubic angstrom. If you have something that is minus 10 electrons per cubic angstrom, probably not good, okay? Maybe you assigned a wrong atom in that position. Maybe you assigned an atom where there is none, but something isn't right. So, what does map resolution look like? Here's an example. There's a structure, okay? Nice little organic molecule. Here is what those electron density maps look like depending on what your data resolution is. Here's 6 angstrom data. Anybody want to work with that? Not really, right? Now, those of you who are about to embark onto protein crystallography, in the cases of really complex proteins, protein complexes, membrane proteins, some of those really big monsters, this may be all people get, okay? Guess what? You need to know a lot about your material and a lot about your crystallographic data to make anything out of it. Now, if I actually had my structure, for example, from NMR or from protein sequencing and other knowledge about what kind of protein peptide sequences usually form helices and stuff like that, if I was really forced to, I could probably get something that at least approximates this model, right? Because this is obviously the bigger ring, and so this has to be the side chain. What I wouldn't be able to tell is this the side chain of that ring or of that ring, okay? But I could still do some kind of placement there if I knew exactly what my atomic connectivity is. Yes?
Once crystals form with larger proteins, is there a way to break it up with better resolution, or once the crystals form, we can push them?
See, the main problem is that usually the proteins have enough disorder that you just don't get data to high enough resolution, okay? So your answer would be grow bigger and better crystals. Unfortunately, that's not always possible, okay? Or use better X-ray sources. That's why a lot of people go to synchrotrons. If you can, by all means, get the better crystal. If that is not an option, you've got to live with what you have, okay? That's the compromise that people have to make. Now, if you have a good protein crystal, you may well get something that is 2 angstrom or better resolution, okay? Here's a 2.5 angstrom data set. Once again, if I knew nothing about what this material looked like, I wouldn't like that one, okay? Quite honestly. I'm sorry, but yeah, there's some blob here and there's something extending somewhere, but if I knew nothing, I wouldn't be comfortable putting atoms into that map. I know that molecule. Could I put that molecule in here? If I knew exactly what the molecule looks like? Probably, right? There's obviously a ring here. There's something sticking out of the ring there and there. Something short and something long. Well, there's a ring, there's something sticking out, something short and something long. So yeah, it's not pretty, I agree, but you could place that molecule. So that shows you that indeed, if you have data that is about 2 angstrom resolution, you might be able to work with it if you know your atomic connectivity, okay? Because then you can define this thing as a unit, and you let the program refine how the unit should be rotated, where it should be placed. How about we get some better resolution data? Here's 1.5 angstrom data. That's starting to look not too bad, right? I think most of us would be willing to assign something there. And there are some proteins that do scatter that well, okay? That's when you can really start looking at what are side chain orientations, things like that. So that would still certainly already be pretty useful. However, it's kind of tough. If you didn't know where the nitrogen is in this ring, would you be comfortable assigning it? No, right? How about this data set at 0.8 angstroms? There are 6 atoms very clearly, and one of them has more electron density than the other ones. It's your nitrogen. There's your fluorine. It has more electron density than this one. There's another nitrogen, once again, has about the same electron density as that one. The oxygen has a little more. That is a beautiful map. Okay, that is easy to work with. Even without knowing anything about your molecule, you could figure out what that is. Because if we have a ring system like that, probably carbon is the most abundant element. Okay, then we need something slightly heavier in there. You could just try. Is it nitrogen? Is it oxygen? What is it? This is the resolution that your small molecule crystallographer would like to have. And that is why if you give somebody who's a small molecule crystallographer a crystal that does not scatter to about 0.8 angstrom, they'll tell you this isn't a good crystal. Okay? So in ideal world, you want that crystal that scatters there. And if it isn't too much effort, go back and try to make a crystal like that. But if that doesn't work, you can probably live with some not quite as good data. Christoph is grinning because he is trying to do that right now, right? How far does yours scatter?
Actually, I don't really know because we didn't look at the
Probably doesn't scatter quite as far as 0.8. Okay, it was a very small crystal. So that happens. You can probably do something with the data, but in an ideal world, you want this really high resolution data. Okay? So, that's your Fourier maps. Even on these maps, locating a light atom can be really tricky. Okay, and once again, what's a light atom? Well, it depends on what your material is. One thing that is always true is hydrogens are really difficult to find by X-ray diffraction. And the reason for that is X-rays are scattered by electrons, and hydrogen has how many electrons? 1. If it is covalently bound, if the bond is polarized somehow, it has less than 1. Okay? That does not make it easy to locate. In some cases, you can overcome this problem by using neutrons, because the neutrons do see the hydrogen. Okay? In some cases, you might actually have good enough X-ray data that you can see the hydrogens. In other cases, you will just make use of the fact that you have some idea of what a carbon-hydrogen bond distance should be. Okay? So you can put in some restraints on where those hydrogen atoms should be, and the program will just place them there. And you'll learn that once you actually do the single crystal project. Here's a really good map. Okay? And this is a difference map, so the atoms that were placed there, that's subtracted from the original data. And in this case, you can actually see 2 residual peaks. Okay? That's where the hydrogens are. Rarely will you see such good data. This is a textbook example. Okay? This is what I was referring to when I was saying there will be some residual ripples. Okay? There's some residual positive density. There's some negative density, which is what these dotted lines are. Part of that has to do with electrons that are bonding. Okay? They are not centered in the ball of the atom. This is what the Pinkerton group looks at. Okay? They are actually dealing with this stuff that we usually ignore. Where's the bonding? Where are the electrons? How is the molecule polarized? You can see these things if you collect good enough data. Is that a routine everyday task? No. Are most of you ever going to do that? Probably not. But it's possible. Okay? Now, at this point in time, we'll actually do a Patterson, as I promised you, okay? I think it'll be very useful to actually get some idea of how you deal with the data. Because all that talk about Pattersons and locating atoms and stuff like that kind of only starts to make sense when you actually have to do it yourself. So, actually we should probably leave that down. This is actually an example from the textbook that I recommended for this class from the lead and Palmer. Okay. Wow, is that all the brightness this thing gives us? That's not very good. Oh well, I guess that's about the best we currently get, so we'll have to live with that. So, there's some information on a compound called KHG2. Alright? What do you think the heavy atom in that compound is? Mercury? Pretty good idea, right? Mercury is pretty heavy. Atomic number of 80. Potassium, what does potassium have? 19. It's a lot heavier. So, Hg will be the atom that we are looking for in the Patterson. What else do we have here? We have some crystal data, okay? It's an orthorhombic crystal system. Unit cell dimensions are given. Unit cell volume, approximate density. And they calculated a number of formula units per unit cell based on the experimental density actually. Okay, so they measured it. 3.99. Well, we know it has to be a whole number, and that's pretty close to 4. So there's a good chance that our Z is 4. That means we have 4 potassium and 8 mercury atoms in the unit cell. Okay, that's what that means. Somebody also did the job for us and figured out what the reflection conditions are. Isn't that nice of them? What they saw was that on HKl the condition was H plus K plus L, and on HKO it was H comma K, on HOL it was H plus L, and OKL it was K plus L. And here's a portion of the table for orthorhombic. And it's only a small portion because this reflection condition means it is a body-centered cell, right? H plus K plus L on HKL means body-centered. So it has to be somewhere in this portion of the table. You can ignore the other 2 pages, luckily. So let's have a look at that and let's see whether we can figure it out. So as I said, we are certainly somewhere in this region based on the HKL condition. Really doesn't matter which of those other 3 conditions we check next, okay? But we may as well go in order. So the next column is OKL. What's our OKL condition? K plus L, right? So that means a whole bunch of them are out. Here are the ones that are still possible. Okay? That's K plus L, the red highlight. The other ones have K comma L. We don't have that condition. So we're already down to basically 4 entries by checking the second condition. Alright, HOL, H plus L. How many of our lines are left? Well, it would be 5 if we checked all of them, right? But we only have to look at the ones that we haven't excluded yet. So there's one, this one, nope, doesn't work, right? This one doesn't work, and this one actually had a K comma L condition there. So the rest of the table is out. So we are left with 2 rows, and we have 1 condition left. HKO, H comma K. Well, one of these has H plus K, one of these has H comma K as an entry. So, this is the one that we are looking at. Pretty easy, isn't it? To figure out what your possible space groups are. So there are two entries here, IM2A and IMMA. And based on looking at the Patterson and at what kind of places you actually find features, the authors actually decided for you that most likely this one crystallized in IMMA, not IM2A, okay? So, we know what space group we are dealing with. Alright? Now, up to here, not too much new stuff, right? We've looked at reflection conditions before and figured things out. Now it becomes important that we actually at some point in time talked about the international tables and what all these things in there mean. These are some pieces from space group IMMA. And this is the point where if you want to look at a Patterson map yourself, you need to know something about this. Okay? Here are the space group diagrams. And they are useful if you want to figure out where atoms sit. But the really important part is this one, our table of positions. Now, IMMA itself has a pretty high multiplicity, like most cubic space groups. However, we don't have to look at the entire table. Anybody got any idea why? Well, we don't necessarily have to look at MM2. That's just one of the special positions, okay? But why do we look at a special position and not at a general position? Well, it's IMMA, but IMMA has more than these positions, okay? IMMA has positions that have a much higher multiplicity. General position will have a higher multiplicity. We have K4HG8 in our unit cell. So, can that potassium sit on a position that has 16-fold multiplicity? No, because we would have too many potassiums. Same for the mercury. So that's why the only part of the table that I'm giving you here on this transparency has 4 and 8-fold multiplicity. Okay? There's no point in looking at something with higher multiplicity if we don't have enough atoms to fill those positions. So that's why it is important to know your Z. Now, where could the mercury sit? Well, could sit on an 8, or another 8, or another 8, or it could sit on 2 4s, right? Because 2 times 4 is 8. So while this is only a portion of the table, it's still a heck of a lot of possibilities, isn't it? This is, we are knowing something about your chemical bonding. It's quite useful, okay? So far you might have thought that physicists should really be the only ones doing crystallography because they like all the math, right? Well, knowing something about the chemistry can help you too. And that's why it is important that you were given the unit cell constants, okay? Your unit cell constants, 8.1, 5.16, 8.77 angstroms. What's the shortest one? 5.16, the B-axis, right? Now, mercury, pretty big element. So, what would be a reasonable distance from one mercury to the next? Well, if we didn't know anything, we would probably just look up atomic radii, something like that, right? And I can tell you one thing, 2 mercuries less than 3 angstroms apart, not likely. Okay? If we know that, then we certainly know that anything that is 1/2 or less along the B-axis would not be a good idea, right? Because 1/2 of the B-axis is what? About 2.6. That's too close for a mercury-mercury distance. Okay? Now, if we know that, okay, for example, if we go here and let's say we take, which position should we take? We could, for example, take this one, okay? G. First position is x 1/4, 1/4. Second position is x 3/4, 1/4. What would be the interatomic distance between these two atoms? 0, 1/2, 0. That would be one of those where the mercuries would be too close together, okay? So, not a good option. And the same will hold true for quite a few of the other positions, including some of the combinations of two positions, 4a and 4b. Look at the first two atoms. Again, you get 0, 1/2, 0 as an interatomic distance, okay? So a lot of these can be excluded just based on your knowledge of what reasonable interatomic distances are, okay? And what you will figure out if you go through this whole series of things, okay, is that there are really not that many options left. What you end up with is that one option is it's H, one option would be A plus C, and one option would be B plus E. Everything else directly from the atomic positions gives you that 1/2. So that's a lot less options, isn't it? Right? So, what do you do at that point in time? Actually, it's A and E, not A and C. I'm sorry. Bad handwriting. What do you do at that point in time? Well, you go ahead and you try some of these out. Okay? What if it is the A and the E position? Well, A and E. So this one and that one. First of all, we can form some interatomic distances between A and A, right? First atom is at 0, 0, 0, second one at 1/2, 0, 0. Nicholas, can you give me the interatomic distance between these two? 0, 0, 0 and 1/2, 0, 0 would be 1/2, 0, 0. Absolutely. Okay. So, that means we should see a peak at 1/2, 0, 0 in our map, right? Isn't that what it means? Well, now it's actually time to look at our Patterson maps. Here are two of your maps, okay? This is a UW map. We just figured out there should be a peak at what? 1/2, 0, 0, right? And this is a projection. So you're looking down the v-axis, you see everything in that cell. If there was a peak at 1/2, 0, 0, there should be a peak at 1/2, 0, 0. Is there a peak here? So that's not a good position, is it? Because just looking at A, we really don't find that atom, do we? So, it's obviously not A and E, okay? And you will find something very similar if you try to do B and E. Okay, because B gives you the same thing. You should have a peak there at 1/2, 0, 0. There is no peak there. That really doesn't leave us many options, does it? That means our atom is in H. Okay? Position H. So let's write down some of those positions. And so that we can actually see what we are doing. Correct? That looks pretty good. So there are our positions. And what this plus and minus means, it's a centrosymmetric space group. So you also have atoms at x bar, 0, z bar, minus 1/2, plus x, 0, minus z, and so on. Okay? So there are 8 atoms that correspond to position H. 4 of them are listed, the other 4 you get by multiplying everything by -1. Let's figure out some interatomic distances. Okay, and this is because that's the most important part of a Patterson. So we will be taking turns. Everybody can do one. And why don't we call this one 1, this one 2, this one 3, this one 4, and start with that. Okay. Nicholas already did one for us in 4a. So, Indira, between 1 and 2, what kind of interatomic distance do we have?
Half minus 2.
1/2 minus 2x, 0, 0. So what Indira did was she took number 2 minus number 1, vectorial subtraction, okay, 1/2 minus x minus x, 0 minus 0, 0, z minus z. So, Anthony, 3 and 1. Is it?
Oh, okay, 1/2 minus 2x.
1/2, yep.
Yeah. 1/2.
1/2. And
that's 1/2.
at 1/2. Pretty boring, huh? Very useless. No x's in there, no y's, no z's. Nate. Minus 2x. 1/2. All right. Adam. So you subtracted 3 from 2, but that doesn't matter because it's the same thing, right? Whether we look this way or the other way, it's still the same distance. All right. Anil, you get 4 minus 2. So the atom at x bar, 1/2 plus z, and 1/2 minus x, 0z. Is it plus 2x? Minus x minus minus x is? So the x drops out. Another one of those boring, useless ones. Chris, 4 minus 3. One half minus 2x. Which are you subtracting from what?
Okay.
Minus 1/2 minus 2x, right?
0.
All right. So let's see. So Stephen gets to do this and its symmetry equivalent one. Very good. And Shu gets that one and this one. And for fairness sake, Christoph, you get to do one too. So that's how you get your interatomic distances. Does that make sense to everybody? Seems like people are pretty good with that. So here's a list of interatomic distances. Okay? And of course now the question is, which of these do we actually use, right? Part of that depends on what we have in our Patterson. Just for the fun of it, I actually printed a slide with a whole bunch of them on them. And I highlighted a few in gray that will be useful, okay? Now, the main thing to keep in mind is we need to look at the Patterson, okay? Because that is really what tells us where our peaks are, and that is what we need to use to do some math. And I once had a ruler. Ah, well, it seems that the ruler got lost. Very sad. Ah, there it is. Good. So, for example, we had some interatomic distance that is 2x minus 1/2, 0, 0, right? That was one of the ones that we determined. I don't remember who did it, but we got that one. Now, if we look at this map, one thing to keep in mind now is that this corresponds to U VW, right? Because that is what our Patterson coordinates mean. Interatomic distances. So V and W are 0, and U is equal to 2x minus 1/2. Right? That is what that one means. Now if we look at this Patterson map, the projection in UW, then we have to ask, do we see any peaks where W is equal to 0? Well, it looks pretty good, right? There are 2 peaks up here. And which of these 2 we take really doesn't matter, okay? Remember, we have more than one atom in this unit cell. Which one we find first and then generate the equivalent ones really doesn't matter. But it's these peaks that we have to take, okay? So, how do you do it? You use a ruler and you plain old-fashioned measure. And remember, we give things as fractional coordinates, right? So one of the things we measure is the total distance between 2 unit cell axes on this drawing. And that's actually 7 centimeters, so it's about 7.05, okay? And then we have to measure to one of those peaks, okay? And let's take the first one. This is 2, 2.5, 2.6, 2.7, it's 2.8. Okay? So that's how you get values out of your Patterson ruler. So, U for this peak is equal to 2.8 divided by 7.05. Okay, that's your fractional U coordinate. And if anybody has a calculator, we can actually figure out what that number is. .397. All right. So what we now know is that 0.397 is equal to 2x minus 1/2, right? Because that is what we know from the Patterson map has to be that interatomic distance. Can we solve that equation for x? For what? 0.448. We just determined one of 3 coordinates of our heavy atom. Is that pretty good? Yeah, right? So, what else can we do? Well, we need more than one coordinate, right? So we need some kind of a z coordinate. And there's obviously peaks along this z, unless I'm much mistaken, right? There's also coordinates along z in other places. So let's look back at what kind of interatomic distances we have that involve z. Well, there are some that involve x also. So they make our life difficult, right? Because we first have to figure out where the heck we actually are. And conveniently, there are some that only involve z. Do we like those? So 1/2 0 2z would be a good one to use. All right. So, where in this map are we looking? We are looking in the middle, right? Because U is 1/2. Does everybody see that? That's where we have to look. U is equal to 1/2. Do we have any peaks here? Yeah, we have two pretty good peaks, right? How do we approach it? Same way. We need to measure what the total distance is. And that would be 6.9, okay? And if we take that peak up here, then that would be about 2.25. And that will be equal to 2z. 0.3? Okay, so we already divided by 2. 0.163. We got a second coordinate. Not too bad, huh? Making good progress here. So what are we missing? The y coordinate. And if we look at our complete list of interatomic distances, what do we say? Does life suck? There's no y coordinate in that whole table, is there? Well, there's a good reason for that, okay? Don't start to be scared. What position did we start working with? That one, right? It's a special position, okay? So, our y coordinate is not y. Our y coordinate is 0, okay? So, our atom is sitting at, as we determined, 0.448, 0, 0.163. Okay? And then you could apply these operators and calculate 8 different atoms. Just by using this X and this Z. Does that make sense? So we've located 2/3 of the atoms in KHD2. Wasn't too tough, was it? So this was something that people could do way before they had powerful computers. Okay? That's why Patterson maps were very important, and they are still used nowadays. So, I hope that gave people a slightly better feeling for what a Patterson is, what it is useful for, what you can do with it, how you approach it. All right. Now, Patterson maps are still in use nowadays. Most computer programs for single crystals actually have Patterson implemented as one of your options for solving things. But you can't always do that, okay? Sometimes you have to do other things. And the rest of this lecture will introduce to some of those other things. What else can you do to play and get initial phases for some reflections in your structure? One that is especially popular with the protein community is isomorphous replacement. Okay? What this boils down to is the same assumption that the Patterson made, which was, if I have a structure that has only one heavy atom, that heavy atom will have a significant contribution to my scattering. That makes sense by now to all of us, right? And they say, well, we could then express this as our F1, our structure factors for this derivative that has a heavy atom in it is equal to the contribution of that metal 1 plus the contribution of the rest. Okay? So this just splits that one structure factor into two portions. One that has only the contributions of the heavy atom and one that has the contributions of everything else. And hey, these are vectors. We are allowed to take several vectors to come up with one, right? It's not a problem. After all, we could add vectors for all those individual atoms together. Oh yeah, that's what we do anyway when we calculate structure factors. So we may as well take it apart, write them separately. And right now that may not make a lot of sense, okay? But that is the starting point for it. And that will be useful. And if we can actually make two structures that are identical except for the fact that they have different heavy atoms, we get a second data set, okay? Which we call F2, that's our measured data. And we can say this one has a contribution from its heavy atom, but it has the same rest, right? Assuming that they really have the same structure, the only thing that changes is the identity of that heavy atom. That's all that changes, nothing else. And then we can calculate a difference map between our two data sets, where we say F1 minus F2 is equal to Fm1 plus R minus Fm2 minus R. Oh, the R drops out. How convenient. So the difference map really only shows you the differences between the two heavy atom contributors. Well, that makes sense if everything else is really the same, right? So, what good does that do us? Well, we might be able to locate that heavy atom from a Patterson, right? So we could actually calculate the positions and thus the phases for these two contributions, right? So we would have the magnitudes of F1 and F2, and we would have the magnitude and phase of Fm1 and Fm2. And that can sometimes allow us to figure out what the phases for these F1 and F2 values should be. How? Well, as I said, we first locate that atom, we calculate the phases for Fm1 and Fm2. And this, for example, is important for proteins because while the heavy atom has a significant contribution to the scattering, you probably have enough electron density out there that it is not the only contribution that counts, right? I mean, if I have something where the total number of electrons besides the heavy atom is less than the number of electrons of the heavy atom, then the heavy atom truly dominates the scattering. If I have a protein, big protein, and there's one heavy metal in it, or maybe two, is that going to be the major contributor? The rest of the electron density is not as localized as the one in the heavy atom, but if you look at the total number of electrons in a unit cell, that heavy atom is no longer as dominant. Okay? So that's why you might have to play these tricks. So we can calculate these completely, and we know these values, the structure factor magnitudes, from our experiment, because that's what we measured, right? Or we measured intensities, but we take the square root, we get these. Now, if you should be lucky and have a centrosymmetric structure, and of course that doesn't happen all the time with proteins because they're usually chiral, but just for simplicity, let's look at a centrosymmetric structure. In that case, your phase would be 0 or 180, right? That's the only options. If you know Fm1 and Fm2, phases and magnitudes, and you know these magnitudes, you can assign phases for these. How? Well, here's a little table that gives you a few examples. Here is your Fm1 minus Fm2, and you know what your sign and magnitude is, okay? If you have these values here, there's only one way of assigning your plus and minus to actually get a correct answer. Plus 3 plus 9 is equal to 12. Plus 3 minus 9 would not be equal to 12 or minus 12. Okay? Minus 3 plus 9 is equal to 6 plus 6, while minus 3 minus 9 would not be equal to plus or minus 6. Okay? And there are a couple of other examples. So as you can see, there's only one way of choosing these two signs, if you know this one. So you can uniquely assign all of your phases. And most of the time the computer is going to do that for you. But this was an important discovery, especially before you had computers. Because you didn't have to do trial and error. You could actually assign your phases. Okay? So, if you're approaching crystallographer, you'll probably hear about isomorphous replacement again. It's very important. One of the ways people do it is a lot of the proteins actually contain water. Right? You could replace some of that water with potassium. Of course, you also have proteins that have a heavy metal in it, and you might be able to substitute a different heavy metal in it. Okay? So there are many ways of doing it. Things work out according to your liking. You'll have a native protein and a protein with a heavy atom in it that have the same structure. You can use a very similar equation to what we had on the last slide. In this case, I chose to call it FPH, which is a protein with a heavy atom in it. It's equal to F of the protein plus F of the heavy atom. Okay? This little drawing just shows you what that is. You have the contribution from the protein, you have the contribution from the heavy atom, and you have your resulting vector. Okay? Problem is, we don't know the phase of that, we don't know the phase of that. We can get the phase of that by locating the heavy atom. So what can you do? Well, you can actually do a little drawing. Real and imaginary axis, Argon vector diagrams should look familiar by now. And you draw a circle around 0 that has a radius of Fp. Because you know what the magnitude, the structure factor magnitude of your native protein is for that reflection, right? So you know that your Fp has to lie somewhere on the circle, but you don't know where. 360 degrees of options. Well, we then grew that heavy atom derivative and we located that heavy atom, and we can actually assign a phase to that FH, because if we know the position we can calculate that. So we can actually draw one precise vector, and we'll be drawing minus FH because what we had originally was FPH is equal to FP plus FH, okay? However, we are after this one, so we just rearrange that equation and say Fp is equal to FPH minus FH, okay? We already drew the Fp over here. So now we've drawn minus FH, now we have to draw the FPH. And that means we draw a circle around the tip of this vector with a radius of FPH. Does that make sense? That's how we sum vectors after all. So there's your circle, radius FPH around the center of H. There are only two places where minus FH plus FPH is equal to FP, which is the intersection points of these two circles, right? So now we are down to two possible phases for your protein. It's either here or there. Now that's already a big step forward compared to it could be anywhere on the circle. It's still one possibility too many because we would like to have one solution, right? So what can you do? How about we grow another heavy atom derivative and do the same thing? Because our chances of 3 circles having 2 common intersection points, not very high, right? So if we do that, oops, we get something like this. Same thing as in the last slide. You have your circle FP around 0 minus FH1 in this case. We had to designate somehow that it is the first one. You draw a circle around here, radius FPH1. Then you do the same a second time. There's your minus FH2. Then you draw a circle with radius FPH2 around the tip of this vector. Okay? There's one point where all 3 circles, well, there's actually one point where 2 circles intersect, one other point where 2 circles intersect, and then there is an area where the 2 intersection points are very close to each other. This was done from real life data, okay? That's why you don't get one exact intersection point for the 3 circles. There's error in your data. But obviously these 2 are much further apart than these. And remember how I said even if you're close in the phase, it usually will actually work pretty well? This is certainly close enough, okay? So you could give a range for your phase angle from this to that. And probably you would just take an average value and use that one. You have just assigned a phase to your FP, okay? You can do that manually. Obviously nowadays computers do the work for us, but this is how you could actually figure out your phase if you have heavy atom derivatives. All right. So that sounds beautiful, right? But there's a what if to it. What if you simply cannot prepare several derivatives? Could be that other metals just don't go in it, right? Proteins have a mind of their own. Or you actually get a different metal in, but your isomorphous material chooses not to be isomorphous. That's when life really sucks, okay? Because you went through all the trouble, you optimized the conditions, you got pretty crystals, and the thing just doesn't crystallize in the same structure. Dang. You could alter just the structure. In some cases you'll even go to a completely different crystal system, okay? In that case you know something is wrong. It's not isomorphous. Or maybe you can put 2 different metals in, but the 2 different metals aren't all that different. They have very similar numbers of electrons. All of these would be reasons why your beautiful isomorphous replacement, as demonstrated on the last couple of slides, would not work too well, right? So what do? Give up? Some people give up, some people say, there has to be something else, right? And yes, there is something else. There's something called anomalous scattering. It's a very elegant technique that can sometimes give you very useful information that you can get no other way. Remember, every atom is represented by its form factor F, right? We've talked about that quite a bit. We said that one is unique for each atom. And so far, we've simply assumed that it is a function of the scattering angle only. However, if you remember when we first introduced it, we did say it also depends on the wavelength. And we kind of didn't really talk about that in detail. What it really is your F has several contributions. Okay? It has an F0 that simply depends on your atom. And then it has these components, F prime and F double prime. So your F should really be properly written as F0 plus delta F prime plus I delta F double prime. Ooh, another complex quantity. The reason why most of the time people ignore this is because F prime and F double prime show hardly any dependence on the angle, so they're kind of just a constant, okay? matter, F double prime most of the time is close to 0. So most of the time you can completely ignore this contribution. Okay? The one time that changes is if you are close to the absorption edge of the atom in question. That is when your F double prime becomes not 0. Now, what does that mean? That means you change your wavelength, you change that one, which really means you change that one, right? Now, if I change the wavelength, I still have an isomorphous crystal, because it's the same crystal, right? Nothing has changed about the structure of that crystal. But I can make it look very different by changing the wavelength. Because if I get close to the absorption edge of the atom, that one here changes. So it has the same effect as substituting a different atom into it. That's very powerful, because you grew one crystal, you've done your job. Okay? Now, what does this F prime and F double prime stuff actually look like? Here's a plot for one element. I chose iron in this case. Okay? Here is your X-ray energy or the X-ray wavelength. They obviously correspond to each other. And here is the iron K edge. Okay? F double prime actually mirrors the absorption edge of your atom. So usually atomic absorption looks something like this. It is pretty much negligible, not too bad, until you come to an absorption edge, it jumps up, and then it starts trailing down again. F prime is simply the first derivative of this curve. So that one changes a lot too, okay? It's not just F double prime that changes. Both of them do. So if you do a measurement here and a measurement there, you'll get very different atomic scattering contributions from this iron atom. Okay? So, here's the effect of anomalous scattering. The other thing to keep in mind is, remember when we introduced Friedel's law? When we said IHKL and IH bar K by L bar are equivalent? And I said, in general, they're equivalent. Right? Here is the time when it isn't equivalent. Because the reason why we said that it was equivalent was because basically our imaginary components were just perpendicular to each other. So whether we went plus or minus, it really didn't matter. The square of it was still the same. Now here is an example. Here's no anomalous scattering, okay? So there really isn't much of an effect. Here's our little f. Here is our f if there is an f double prime contribution. Well, in one case, that f double prime would be going here. For minus h, that f double prime would be going in the opposite direction. Right? That means our fh and our fh bar are no longer the same. Well, our f magnitude is no longer the same. Let's put it that way. The two of them are different. So Friedel's law breaks down if you have anomalous scattering. And sometimes you actually make use of that. Okay? How does anomalous scattering work? Well, it's the same as growing the heavy atom derivatives. The main difference is you have your minus FH1 and then you have the F double prime contribution in both directions, positive and negative. Okay? And then you have to draw the two circles around these points. But once again, you get 3 circles and you get 1 intersection point. So that's how you get your phases there. That is why a lot of people go to the synchrotron. Because at the synchrotron, you choose your wavelength. In the lab, not quite so easy. Okay? So far we've said we locate our heavy atoms with Patterson methods. But what if we don't have heavy atoms? Well, the second method that is implemented in pretty much all small molecule crystallography programs is called direct methods. So if you have a purely organic molecule, you usually use that one. Or if you have something that just doesn't have a lot of scattering contrast between elements. Prime example would be AlF3. Okay? Aluminum and fluorine seem to be far enough away from each other in the periodic table, right? I mean, one is in the second row, one is in the third row. But if we have Al3 plus, has the electron configuration of neon. If we have F minus, what is its electron configuration? Neon. How good is our contrast between Al3 plus and F minus? Non-existent, right? If they were completely ionic, we would have zero contrast between those elements. So your Patterson map would look rather confusing, because yes, you have the AL distances, which come from equivalent positions. You have the FF distances that come from equivalent positions, but all your ALF distances that have nothing to do with your interatomic distances from symmetry equivalent atoms will also show up at about the same strength. Well, that sucks, to put it very non-scientific, okay? So what do? Well, you use what is called direct methods, and what this is phase probability methods, okay? It makes use of the fact that the electron density has to be non-negative, and of the fact that the electron density should be pooled in atoms. It usually uses the normalized structure factor, so that's similar to the Patterson maps. First of all, you can actually get quite a bit of symmetry information from your E statistics of your normalized structure factors. Okay, and the main thing that you usually look for there is your structure centrosymmetric or not. So that's obviously important for assigning phases, right? Centrosymmetric, it's 0 or 180. Non-centrosymmetric, it could be anything. And there's a lot of theory behind this. I'm not going to ask you to actually go through that theory. I'm not even going to ask you to remember these things. I just want you to know you can distinguish a centrosymmetric and a non-centrosymmetric structure by looking at your statistics. Here's an example, okay? Your E squared mean values should be 1. Never mind whether your structure is centrosymmetric or not, because these are normalized structure factors, right? So if you sum them all up, they'd better be on average 1, because we normalized by the scattering contributions of all the atoms. So not very good for distinguishing centrosymmetric and non-centrosymmetric structures. Your E values themselves, that could make a little more of a difference, right? Because the E squared is what is really normalized. So there should be some difference. Predicted is 0.8 and 0.89. Most crystals don't do you the favor of letting them distinguish the crystal centrosymmetricity by that. But then you can also use E squared minus 1 average values. And that is where usually the computer can make an assignment. These are usually still not completely black and white, okay? It's still a little bit gray. But if I see a value of 0.91, and I know it should either be 0.97 or 0.74, the computer will probably tell you that it should be centrosymmetric at this point, okay? So that's the first step. These statistics allow you to get some idea of whether you have a centrosymmetric or a non-centrosymmetric space group. And that is what the computer will be using. It's not magic. It uses statistics. At that point in time, it then chooses an origin, because all your phase angles are defined relative to the origin. And that origin is arbitrary. You just have to keep everything relative to the same origin. The only thing that will change, especially in a centrosymmetric structure, is the sign of FHKL, okay? But it won't change what your intensity is. If you take 3 reflections and you assign phases to them, you've pretty much fixed your origin. In a non-centrosymmetric structure, you would take a 4th reflection, because you still need to determine the handedness, right? Non-centrosymmetric structures achiral. You then use this initial set of reflections as a basis set for your probability methods. Okay, that is what the computer does. So usually it uses very strong reflections for the initial phase choices, because that just gives you some more reliable statistics. What does the computer then use? It uses something called triplets. Okay, this goes back quite a while. 1952, a guy called Sear actually showed that if you have a centrosymmetric structure, so once again we'll talk about the simplest case, if you have 3 reflections with indices that are related as HKL, H prime, K prime, L prime, so 3 different indices, and the third one, each of the indices is the difference between the numbers of the other 2. This is what you call a triplet. Okay? And what he showed was that the sign, because it's really just a plus or minus sign, what the phase is in a centrosymmetric structure, of the first reflection times the second times the third one is likely to be positive. Okay, so this sign here, it's a probability expression, so it should be read as is likely to be, not really as approximate. Looks like a very simple trivial equation, but this part that comes from probability actually allows you to assign phases to all reflections. Okay? Because once you've assigned a phase to one of these by knowing 2 of the strong ones, you can use that one as an additional part of your basis set. You can keep going. So you can assign phases to all reflections. As I said, these are called a triplet, and their corresponding D star vectors will actually form a triangle, so that's where the triplet comes from. If you know 2 of the signs, you can figure out what the third one is. Now, just a year later, this formula was augmented by Hauptmann and Karl, who actually introduced a slightly more sophisticated equation. But it's very similar. And what they said was, in many cases, I have more than one set of reflections that form a triplet relationship with my one reflection that I'm looking at. And so they basically said that they should make use of all of these reflections that fulfill that, because if we are talking probability, the more reflections you look at, the better your chances of being right. Okay? And that is what they basically introduced. So this is the Hauptmann and Karl sum formula for triplets. And they actually won a Nobel Prize for their contributions to crystallography. Okay? Non-centrosymmetric structures, the math gets a lot more ugly. So we are not even going to go there. The computer does it for you. You probably should have some idea of the fact that there are triplet relationships in direct methods and how they are defined. Okay, what is a triplet? What are these reflections? I'm not going to ask you where that stuff comes from. However, you should know what the computer is doing, at least to a very basic approximation. So how does that look in real life? Well, here are some reflections. There's a 200, a 300, and a 500. Let's assume we know the signs for the 200 and the 300. They are minus and plus. The one that is questionable then is a 500. We could make it minus, we could make it plus. If we make it minus, we fulfill the triplet is likely to be relationship, right? Minus times minus is plus 1. This is what you get. If we assign a plus sign here, which means we would violate that probability relationship, here's what you would get. Okay? So this is just one example that shows you that these methods really do hold. Now, I think that is it on the direct methods. As I said, we are not going to go into details. We are not going to do them manually, although I have seen people assigning reflection phases like it was a Sunday afternoon stroll in the park. It's pretty amazing what some of those old guys can do, because they had to do that themselves in the early days. Okay, 1953, they didn't have many computers around. They're really good at it. Luckily for us, the computer does the work. But this is what the computer does, so that you have some kind of idea of what this is. Okay? All right, any questions about the structure solution part at this point in time? This just gives you some idea of what is done when you work with a crystal, okay? Now, on Wednesday we'll probably be covering the next two handouts because they are fairly short, okay? So bring both handout 12 and 13. And then on Monday we'll have a review. Next week, Wednesday, we'll have the exam. As I said, if you two can send me your 0-point calculation, then the project should be ready for pickup later on today. Overall, people did very good on it. So good job, folks. Might have been work, but you certainly all made it to the right solution. And if nobody has any questions, that would be it for today.